Oh, hey, everybody. Quick question about the 475 Star Wars forecasting project. How much do we stick to with our outline that we put on the repo? My group has a very rough... Yeah, no, you can deviate. I just ended the last stream and I was like getting everything ready here with my Pearson questions. You can deviate. It's a rough outline, Dylan. Dalen. Ah! Dalen, I've done it. I've put your name in my head the wrong way. And now I'll forever get it wrong. It was Spanbauer who said, because I was talking about, I was like, oh, Dylan, duh, he's great. You know, he's doing a lot of cool things. And he's like, Dylan. I was like, hey, swings by your office. You know, Dylan. I said, Dalen? I said, oh. And he was like, I think he just thought, this guy can't read. And that's a true fact about me. True facts about Brian Stevens. He can't read. It's kind of serious. We're getting up. Leo's got some great questions here. Yeah, so thanks to Spanbauer, Adam Spanbauer. I know how to pronounce your name correctly. Hey, Lillian, good to see you here. We got 2 questions. Drop them in the chat. We have first question. Maria says, I need help on the 15 question about the cancer risk from atomic bombs. And chapter 15, nonprofit concerned about the school dropout rates. Leo is wondering about nonprofits. And we've got cancer risk questions. Oh, and 1D. That's from 320, right, Lillian? And the airline. So let me put these in order right here. So we got Stat 201, Chapter 15. Chapter 15, bombs and cancer. Amazing. Stat 201, Chapter 15, nonprofit dropout rate. BAS 320. Assignment 10, right? Is the assignment 10 1D? Identity visualization. Yeah, sure. And philanthropic Christian. Awesome Christian. Thank you so much. Most of them on the campus just know me by my middle name. Because I don't want to risk them botching my name. Oh, 1D. Nice. That's I had people in high school call me by my middle name. For some reason the roll sheet was there and they're like Joseph Stevens. And I was like, and then my friends were like, is that your name? And I was like, I guess. And they're like, oh, wait. So is Brian your middle name? And I was like, no. And they're like, it is, isn't it? And I was like, no, it's not. But no, my friends. Child abnormalities. Awesome. Well, not awesome, but Stat 201, Chapter 15. Child abnormalities. I'm taking all the notes right now so we can... There we go. Yeah. What happens when Brian just has a stream of consciousness as we're just taking notes right here and getting things done. Okay. Cracking Leo up in the chat right there. Leo, you are the all-star. We have talked in other classes about summoning Leo, like you're a Final Fantasy VII summons. Will we go over the project? We could, Jameson. We could do some project. Yeah, the background moves. I've got other backgrounds. We'll look at that real quick and then we'll get serious here. We'll take a half second. Let me change backgrounds. There, my background's gone. Here, we'll use this. That's wrong.
Let's get right into the news.
This week at the University of Tennessee, Brian Stevens taught statistics. What's up with that? I don't know. This is not... We have to remove the background and stuff. We can do this right here. I have other things. Where's my... I can do that. I like the green space best. Yeah. This is my favorite. I might change it, make it more... I don't know. It's like a nice little... Yeah. Okay. Time to get serious. Let's see. First one on the docket is having some fun. Bombs and cancer. Bombs and cancer. One more song. We should be ready to go. Yeah, that one's good. Why not? Okay. Oh, Mubot, are you behind in the times? No, it's behind. Bombs and cancer. Oh, found it. Here we go. Let's start it up. At 5:03, starting it up. Here we go. Fun's over. Time to get serious and show the question. We have right here radioactive fallout and cancer risk. Now, what do we do whenever we get a question? The first thing we do, step 0, as we're calling it nowadays, It's a great day, right? Right. Step 0 is to do what? Step 0 is to do what? Yeah, no, right. See, have fun, Dalen at 474. No. Leo and Dalen, great minds think alike right there. Not to cheat. Notation, brother. So we got right there. If you were to record, Leo, some like you being like notation, brother, I'd like push out my soundboard if you wanted, so we could channel Leo. Your call, of course. And great job right there, Maria, starting us off strong right here on the question, already jumping into it. Remember, the more interaction we have, the quicker we go through the questions. Just want people to practice. That's my goal by asking all the things of what we're doing. So what is the notation? Maria, you have earned all the notation. Make sure to practice this as I do it. We find out that there's 230 people in a region. Maria immediately said that is the sample size. We found out that 26 of them had cancer, and usually people get this one wrong. This is the amount of successes. I know that sounds weird, but it's the amount of observed things that conform to what we're talking about. That's what a success means. It doesn't have any positive or negative connotation in statistics. It's just the idea of the successes. Now, as soon as you see you found x over n, what should you solve for? I'm not going to tell you the name of this quantity yet. I want you to be thinking x over n is equal to what theoretical quantity? What is the theoretical quantity called that I'm solving for? Great job right there, Maria. P hat, which is the sample proportion. So this would be the proportion of people who got cancer in that region. It just kind of makes sense to say, you know, we're just going to solve for this. Oh, no. 41 of them. I am so sorry. Brian's got to slow down a little bit. 41 of them got cancer. I knew something was a little bit wrong. More on that in a second. Brian, slow down, man. Slow down. No rush. 41 of them got cancer. More on the other number in a moment. So this is the amount in the region that got cancer. Oh, I could. You're right. I should try that. I should do some recordings. Now, the other one speaks a little differently. The other one says the amount we would expect. So something we would expect would go with the what hypothesis. What we would expect in a group that size would go with the what hypothesis. So what we would expect in a group that size would go with the what hypothesis. So what we would expect in a group that size would go with the what hypothesis. So what we would expect would go with the null. So we're saying we would expect, and this is where we write the null, we would expect the true proportion to be equal to 26 out of 230. Now, it doesn't write that, and we're wondering, so are there 23, and the cancer estimate that one would expect, So with this right here, could you go start up company? Mm-hmm. So with this right here, this is the expected proportion. And with this being the expected proportion, let's look at the answers we get and notice, what do you notice 26 over 230 is? Now be careful, what is this value in notation? P equals what? P equals what? I want to know what this is called right here. It's the expected according to the null. P equals what? What is that value in notation? P equals what? What is that value called? P equals, not the true, very close. P equals what? It is what we hypothesize is true. P equals, that value we just gave is, so that value that we hypothesize is true, like what we would expect is P naught. That's the hypothesized truth. Does that P naught? So that's the hypothesized truth. So that'll be used down here when we solve the problem in a second. And this is the solving of the problem right here that we are doing. So we have right here where we're writing the null, where we're saying P equals P naught. And the alternative being, does it give us sidedness? That's what I need to see. Oh, is the death rate too high? So by doing too high, which alternative should we use? The not equal, the truth is less than this, or the truth is greater than this? A, B, C. D is not the right answer. Should we say that we're looking to see if that the truth is not equal to this, that the true proportion of people who die is less than this amount that we hypothesize, or the truth is greater than? Because we're trying to see, is it too high? We're asking, is it too high? And the answer would be C right here, because we're asking, is the true proportion of people who died from cancer higher than what we would expect? Try reading it that way. Is the true proportion of people, which that's what that stands for, dying of cancer greater than what we would expect? The expected value, once again, was found by doing the amount of people we expected out of a size of sample that big. And this gives here P naught, which is what we would expect. And we're asking, is the truth greater than what we would expect? So now we do the Z statistic right here. So this is where the notation comes into such a large play, because this is P naught right here. And so let's go ahead and solve the equation. The equation is going to be P hat minus P naught over P naught Q naught over N square root. So we need to write in P naught right here. The 26, that's a weird, that kind of in notation would probably be X naught, which would be the amount of successes we would expect according to the null. I don't think any other problem does that. That's why it caught me off guard, and I marked it wrong on my first thing going here. That would, because like X is the amount of successes, naught being according to the null. So in proper notation, that'd probably be called X naught, which is the amount of successes expected given the null is true. Does that make sense? Which this would be the proportion we would expect given the null is true. That's the hypothesized proportion. These are the hypothesized successes. So putting that little naught right there means according to the null. Like that is, if the null is true, that's what we should see. Or close to. Not see exactly that, but that's like what we would expect given the null. So Maria, great questions. That's the only thing we didn't give like a value to, but that would be X naught. The hypothesized successes. So good questions, which won't be used for this equation, but it helped us find P naught. So now make sure to carry all your decimals by doing this. 0.1130. That is P naught. Can anyone find Q naught for me while I write the rest of this? Can anyone find Q naught for me? Remember how to find Q naught. How do we find Q naught? Find Q naught in the chat. Find Q naught for me. What is Q naught? How do we find Q naught? We have P naught. Great job, Leo. And Leo round up. Great work. 100 points right there. It's just 1 minus P naught. There we go. So 1 minus P naught is Q naught. And let's go ahead and take this and find the Z statistic. Z's are for proportions. So what I'm going to do right here, I think that's enough decimals. We should be good. Okay. So let's do 1 minus times that. That's the top right there. Divide by 230 and square root. There we go. So that's 0.0208. And the top of the equation is going to be, let's see out here. So many decimals. 41 divided by 230. That's that first number. Actually, I should have got the second first. And then 26 divided by 230. Let me copy that. 41 divided by 230 minus, that is, oh wait, no. There we go. That's the difference. Cool. Starting using the Windows built-in calculator, so it's nicer on Pearson. Yeah, with copy pasting. Copy pasting is so huge. And just look at this, make sure it makes sense. We're seeing a difference about 6.5%. So just make sure your numbers are making sense as you put them in the calculator. So 0.065 right there. Make sure to carry all your decimals, as many as you can. 217. And then we're just going to divide this, and we should get a little more than 3.1 or so. So we're going to divide this by 0.02088 and 3.123. So we said a little bit more than 3 because that's like 6 divided by 2 right there, but extra change on it. So 3.123 is the z-score. Now with this z-score that we have, which is step 2, So how many decimals? 2 decimals, so 3.12. We need to find the p-value. And what if I told you I already know the p-value? So Leo, think about this. And everyone here, think about this. If we have right here, and this is on the third step right here. So step 3, this was step 2, find the z-score. We go to step 3, which is find the p-value. And we draw our normal curve right here because it's a z-score. And we go up 1, 2, 3 standard deviations. Our z-score landed right here, which means our p-value is this. Can you estimate that p-value for me right here? Just tell me what percent of the curve have I shaded in. Yep, we're going to be doing that. You bet, Laura. You got it. We got the child abnormalities coming up here in just a little bit. Thank you for asking because we got it on the list. You got it. So what is that? How much is that? How much of the curve have I shaded? And we're going to use the David M. Lane to find out the exact answer. 14 is going to be 505. Ooh. Let me drop a link for you in the chat. 2 seconds, Katie. Mine was 0.0042. That might be. It's going to be small, yeah. And so if you go to the applet, very good answer, Maria, right there. We should get a very small value. We are doing the above right here. And we're going to get a very small value, 0.00009. And look, you can't even really see it off the curve. It's that little tiny. It doesn't even, you can tell it is that. It's that little tiny right there. Little bit. And you can see it better if I do that. Now, that's not the answer. It's that tiny area, and that's 0.00009. So it's very unlikely. Very unlikely. Philanthropic, I think we have that one listed. I'll take a look right here. You bet. And so now let's go ahead and grab that p-value, drop it in right here. Oh, wow. We have to do 4 decimals. Woo! Is the observed death rate unusually high? Well, think about this. Our result was very far away from what we expected. Remember our drawing we made? Here's the null hypothesis at the center of the curve. The null, p0, is here. This is our observed sample proportion. We landed very far away from the null. So does what we saw right here, this is what we saw. So was what we saw close to what we expected or far away from what we expected? Just speak to me as it looks. Was what I saw in my sample, p hat, close to what I expected, my null proportion? Was it close or far away? Would you say like, oh, that's kind of close to what you expected? Or no, that's pretty far away. That's pretty unusual. Like, was what I saw right here, this is the standardized version of it. It's not close, right? It's pretty far away. Like, and then the p-value gives the probability telling us it's very unlikely. So the p-value tells us that this result would only occur due to random chance if the null is true about 9 out of 10,000 times. So it's super unlikely. You're like, no, I don't believe it. So what do you think we're going to do to the AO Carter? Good to see you here. What do you think we're going to do to the null hypothesis? You'd be like, I should probably what the null. Like, this does not look very likely to me. You'd be like, this, not likely. Oh no. I'm going to send you something here, Katie, in a second. Remind me. We're going to make sure we have all the questions written down. Katie, remind me. We're going to reject the null because this is super unlikely. You're like, no, this does not seem likely. The p-value. I have people on my roof. They're doing roof. The p-value is low enough to conclude that the death rate is unusually high, i.e. they're just saying reject the null. The p-value is low enough to reject the null and conclude that we have evidence that the death rate is high. They don't say reject the null. They're just using different words right there, but they are saying the p-value is low enough. So yeah, if the p-value is high, we would not have enough evidence. So the p-value is low. We reject the null. We have evidence that the death rate is unusually high. Because remember, the alternative is that the death rate is higher than what we would expect. Good, Maria, don't worry. Good practice. Good practice. Does this prove? Anytime you hear does this prove, what should you answer? Anytime if this is a good review for the test, if you hear does this prove in statistics, what should you answer immediately? What should you look for? Does this prove? No. Now, be careful. I know you're thinking no. We can't say causation, right? They went a little different route on their answer, but I agree with Casey 100 points. So the no answer says there's insufficient evidence. We do have evidence that there is a connection. We have evidence of a connection. But whether the death rate by cancer is unusually high or not, the cause cannot be determined. Statistics doesn't talk about causality. It just talks about association, whether two things are associated. Or like we have evidence here that the death rate is higher in this region from cancer. So we should get everything right. Come on. What says I haven't done something yet? What? Oh, are the assumptions met? Yeah, sure. Condition 1, random. Condition 2, 10%. And condition 3, success failure. We do have at least 10 successes, at least 10 failures according to the null hypothesis. This would be NP0 and Q0. I was afraid I mistyped something. Is it Katie? Let me hop here to the main screen. We're going to send you something, Katie. Tell me if this works. Woo. Put on this one. Katie, thank you so much. Let me make sure I have all the questions written down. Katie, try this link. Oh, tell me if there's a decimal error, Maria. You got this, Maria. Everyone, give some good vibes towards Maria. Maria, tell us you got that 100. Tell us you got it. I want to hear it. Oh, I just got that 100. Another quiz done. Another 100 out of the way. Tell me if that works, Katie, right there. That's a direct link to the to Pearson. The direct link sometimes will, and then log in, try it right there. Might be some sort of weird Canvas issue. Gotta love internet. Gotta love the internet. We have the non-profit dropout rate. Make sure I have everyone's. Was it a decimal thing? Maria, you got this. Let's throw another 100 points. If it's a decimal thing, let me know immediately. Or if it's one of those questions where I'm like, that one doesn't matter so much. Philanthropic. We don't have philanthropic today. Let me put that. I think we might have done that one yesterday, but we'll put philanthropic on here. Chapter 15. Philanthropic. We have abnormalities. Let's do abnormalities next. Everyone's been asking about abnormalities. I don't think we've done that one lately. We're doing abnormalities next. And I think we're good. Do I do a student or sign in? You do the sign in. You should be able to do it there. Tell me if that works, Katie. Because I don't usually do it. You go to the sign in. You go to the sign in. You shouldn't have to register because you already have this is just the main way to access it, not through Canvas. That should work with just the sign in, and it should do like university sign in. So that's like the actual site that we're connecting to when we link your LMS learning management. I don't know what they're called. Here we go. Let's do the next quiz question on abnormalities. Startup company, airlines, public relations, nonprofit. Wait. That's not abnormalities. Abnormalities. Here we go. Let's do it. It's working. Great job, Katie. 100 points. Go to the main screen. You got it. Oh, that's Maria. You got this. Good practice right there, Maria. I'm going to Maria 500 points. Maria, great work and good practice. Yeah, rejecting, not rejecting. Good practice. Maria got this. These are great ones to get a little extra practice on. Yeah, that's what we're doing right now, Warren. Good questions. We got child abnormalities. Great time to jump in here, Warren. Chapter 15 quiz. And everyone channel Leo right here. What do we got to do? You know what we're going to do. It's our favorite step 0. Before we even get started on writing nulls and alternatives, we always do this whenever we encounter a question. You got it, Maria. You got this. Notation, brother.
Notation, brother.
See, I could wait. Give me a second.
Notation, brother. Notation, brother.
Oh my god.
We have to do this. Notation, brother. Notation, brother. We'll do better.
Okay. So we get it.
Notation, brother.
Okay, so let's write that notation down. Okay, what do we have? Someone help me out with this notation. Someone help me out. I need this help. I need help. I need notation help. Tell me one of the colors. Help me out. See if you know it. See if you can answer what all these values are in notation. In the 1980s, it was generally believed congenital abnormalities. That means you're born with it. Great job, Leo, there, getting the sample size. Would impact about 7% of children. Some believe that the increase in the numbers is due to chemicals. A recent study found that 426 randomly sampled children had 48 abnormalities. This is strong evidence it has increased. So X is 48. So Leo has identified how many children we have sampled, how many children in the sample had abnormalities. And let's do one more, and then I'll do the remaining. So I just need, because we're on to the hard ones now. We're on to the newer ones. This is all the important information in the problem I think I've labeled. All the information, we've broken it down, and we've identified what we need to know to solve this. Everything else is just little salt pan on top. One more thing. Yeah, Leo. Great job, Leo. That is P naught. That is the believed amount. So that is what is generally believed, which is assumed to be true and given until evidence otherwise. That is the kind of starting belief, the initial hypothesis. That is correct right there. And then this is going to be for the sign of the alternative. Has it increased? See, I don't even know what I'm doing. Has it increased? That's going to indicate the sign of the alternative. And then the 0.05 is the alpha level they're using. So now that we've identified all the notation, we know they're looking to reject at a 0.05 alpha level. When if our p-value is below alpha, we reject the null. Our sample size is 426, and the hypothesized proportion is 7%, and we're looking to see if it's increased, and we have an x of 48. One of the things we need to do now immediately is we need to take x over n, which is going to give us the sample proportion. This is just how many observations out of the sample size we saw that conform to what we're looking for. So we have 48 out of 426. And just say there was 11.2% of children with congenital abnormalities. There we go. Have you gone over the visualization? Oh, we did it yesterday. So check out yesterday's evening's office hours, Alexa. We might have time to spin back to it today, but yesterday's evening office hours, we did it. So check that out. Is it this one? There we go. Here's where we did it yesterday evening, so check that out. Good question, Alexa. 100 points. Thank you for asking. But check out yesterday's evening's office hours, and it's labeled in the video. So check it out. We haven't done it today yet, but we might got a lot of problems. Thank you, everyone, so much for being here. It's good practice. So what's our first step now? What's our first step? What should we do now? So if you're in class this morning, we already reviewed this. The first step now is to do what? So now your step one is to do what? Now we're onto this screen right here. We wrote our notation, which I call step 0, like just getting it started. Now we have what? Pretty much, very close, Leo, very close. You're on the right track. So remember, we know what P naught is. We found P naught, so we're just going to put that right there. Does that make sense? So if you write your null, you can write the alternative pretty quickly. So it's going to be P equals, and try to read it as a sentence. Say, my null states that the true proportion of children born with congenital abnormalities is equal to 0.07. So we're talking about the true proportion and making statements about the true proportion of children born with congenital abnormalities at birth. Great job, Leo, on the recovery. Great job, Kaya. Good to see you here. Mubot saying hi to everyone in the chat. But we're going to put right there the value of P naught because we're solving for proportions, which is categorical data. So we'll write the null hypothesis right here that the true proportion of children with congenital abnormalities is 7% or 0.07. And the alternative is based on the way the question is worded, not the data. So we're trying to see, has there been an increase? And the increase is because they're asking that in the question. Great job, Leo. And make sure to put P in there. A lot of people forget that, especially when we've done written tests and CAD. Great work there also. The question or the researcher's question denotes the sign of the alternative. So the next step here is going to be to solve for the z, the t, or the chi-squared. So this is step 1, which is null/alternative. And then step 2 is going to be to solve for the z, the t, or the chi-squared. We haven't done chi-squared yet. We did t today in class, and we'll do it later today if you're in the afternoon class. So it really comes down to writing out your equation of p hat minus p naught over p naught q naught over n square root. This will solve for a z-score, so we need to plug in our numbers that we found. There's the sample proportion right there. It's at the top of the screen, the p hat up there at the top, found by x over n. I haven't written down q naught, but what is q naught? Someone drop it in the chat right there. It's very easy once you know how to get q naught. What is q naught? A lot of people say, well, wait, what is q naught? How do I find q naught? What is q naught? What's q naught? I forgot p. Oh, we don't know p. Oh, you forgot the p. Yes, exactly. Dad, you're exactly right for the notation. Sample size is 426. I'm on top chat. Oh, what is q naught? Q naught is 1 minus p naught. So q naught is It's just whatever adds up to 1. So if you look right there, Q naught, if you times Q naught, or if you add Q naught and P naught, they add up to 1. So you just simply think what adds up to 1, or you subtract. If you want to be certain, take P naught and go 1 minus P naught. Doesn't hurt to put in the calculator. 320. Yeah, we're supposed to. Yeah, Micaiah, we'll do that right here. We're going to do some 320 here in a moment. Got an hour left about. So yeah, you bet. Let me write that down, Micaiah, because we have a 320 question also. So we'll try to do both those because we have another 320. Assignment 10. Question 2. B3 to B5. Yeah, we'll take a look at that. We'll do parts of them. That sounds good, Micaiah, right there. Good stuff. Thank you, Micaiah. We'll probably do a 320 after this because we try to mix it up and have every class do some work. So now let's find our Z. Our Z is going to be 0.07 times 0.93 divided by 426 square root. That's the standard deviation on the bottom. I just found all this value right here. Now the top of it is 0.11267 minus 0.07. And the Z-score is 3.45. So this Z right here is 3. Does anyone have a guess of what the p-value is? Next step is to find the p-value. And I know the p-value because of what the Z-score is. Because when I do my drawing, I go here and I go 3 standard deviations up, and I realize I'm all the way over here. And the p-value is going to be this area. Now, the reason I'm shading to the right is because the test up here up top is the greater than test. So the test up there, which we've shaded right here, tells us which way to shade. So since it points to the right, we shade to the right, and you just have a guess of what that p-value is. We can probably just straight guess the p-value because of how extreme it is. The p-value is the probability of what we saw in our sample. So when you think about how much area this is right here, it's basically nothing. As my friend Ned used to say, nothing at all. Nothing at all. So when we look at a p-value that's basically nothing, it's going to be very, very small. And we can go over here to the applet, and we would have you kind of estimate, or you would be able to guess this on the test. We might give numbers like, is it 10%? I mean, if you look at it visually, let's go look at it again. We could ask you, is the p-value here like 10%, 20%, or is it close to 0? And the answer is the p-value. That's not the Z statistic. The p-value is going to be basically 0. It's off the curve. It's so small, you can't even see it. We can't even see. I think that's it right there. I can't even tell. But this plots the area above it, and this is very tiny right there. You can barely see that. We're talking about the area above 3, which is that. It's not, you see, this is not shading anything. That's the area above 3. Makes a little more sense if I do it something you can see, like 2.6. But we're talking about the area that is probably above, like right there, which is so very little area. It's basically invisible. So it might have even accepted 0, and this is a rough sketch of what we should be looking for when we do the applet. So now that we have the p-value, let's do the rest of the question right here. We've basically solved everything and done the steps on our own. Now, we would say that the null is that the truth is equal to this, and we're looking for evidence that it's greater, and we wrote that ourselves. The conditions are that it needs to be a random sample, it needs to be less than 10% of the population was sampled, it needs to be independent, which basically means random, and there needs to be more than 10 successes and more than 10 failures. Really good review right here, except we put together the independence and the random because if it is random, it's independent. So we just combined this into the idea of it being random. So if you're wondering, they just split it apart right there. But if it is independent, it'd be random. If it's random, it should be independent. Good stuff right there. Now it jumps straight to the p-value. I think that's where usually people get confused on this. And it wants to 3 decimals, which interestingly enough, it should be 0. Hopefully I haven't done anything wrong. Let me look at the numbers again. That does look to be accurate. It does look to be accurate. We'll find out. But the p-value is basically 0. And since the p-value is low, what are we going to do to the null hypothesis? Since the p-value is low, no, they want to know what the p-value means. The p-value is the probability of observing our results or results from our stream, assuming 7% is true. And right here, if 7% of children actually have congenital abnormalities, then this would be the probability. Let it go. Exactly, great job. But the p-value is low. Just let it go. Oh my gosh, I like that kind of better too. If the p-value is high, just let it fly. Let it go. We should have done that. Should have done that with all the, what is it, frozen stuff? So this right here tells us that the p-value is the probability of observing our results, because it's a probability, the chance of observing our results given the null is true. Very important. It's always conditional on the null being true. And so the p-value is low, so we reject the null. There is sufficient evidence. Now take a look. We've got some notes from earlier in our class where when we reject the null, it's because there's evidence. Now I have red right here because that means you're rejecting it. So if we reject the null, there is evidence for the alternative, or the second scenario, if the p-value is high, we fail to reject null, which means we're staying with it. We do not reject it, and we do not have evidence for the alternative. The alternative is the evidence-based claim. So make sure you understand the statements of, I reject the null, like I reject Brian is innocent, I have evidence of his guilt, or I do not reject, i.e. fail to reject that Brian is innocent, I do not have evidence of his guilt. So this is important to see right here and important to understand how we speak. You reject the null because there's evidence for the alternative, or you do not reject because you do not have evidence, known as fail to reject. So I reject the null, there is evidence for the alternative. Do environmental chemicals cause? Now, cause is like the word prove. Like, do they cause or prove? And we can't say that. It is unknown if environmental chemicals cause congenital abnormalities because the hypothesis test does not indicate the cause of any changes. Oh, I got so afraid. Just gotta. Sometimes I'll like triple check problems. But yeah, good stuff. Just make sure to do your math correctly. And yeah, good problem. Tough problems, a little bit of a long solve. But work through the problem, and this is a very low p-value, so you reject the null. The p-value is low here. I reject the null at the 0.05 alpha level, and they even specified that there at the top. Since the p-value was below 0.05, we reject the null. The last step is, if we work through this classically on a sheet of paper, would have been to go here and to see that our p-value, hey, James, good to see you here. Yeah, we're about to do some 320 in a second. Leo, definitely nonprofit. Leo, we'll put that next. Thank you so much, Leo. The p-value of 0.003, we're going to do a little, it was this, is below our alpha of 0.05. And since the p-value is below alpha, we reject. Ooh, looks like a lot of good stuff on nonprofit. Let's go get the sheet out here. We've got, yep, nonprofit dropout rate. I'm going to do, which one did James want? C3. So the first question for 320 was D1. We're going to do a 320, then Leo, we're going to do that next, and then we'll probably do another 320 after that. So we've got it on the sheet right here. Thank you so much, everyone, for being here. I appreciate it. Let's hop back to the main screen. More 320, or a little 320, then some 201. Leo coming right up here with the nonprofit question. Here we go. Thank you so much, everybody, for following along and practicing. We are going to get some logistic regression. So 201, you've heard of regression, but now it's time to do logistic regression. This might be a quick question. You never know. Okay. Let's see right here. We're going to do some logistic. Clearing out the screen. Okay. Oh, that was such a cool graph. I should have left it up there. Here we go with a little logistic. And the timestamp is... I'm doing 2 questions. Oh my God. 38 followed to 4. Here we go. On logistic regression, another strong predictor of account age is the number of months since the person's first donated. Fit a model predicting last amount from recent average accounts age and setting and the interaction between these variables. Examine the coefficients and the results of the drop 1. Okay, so we're going to load in. This loads everything above right here. We already have where it's loading the data. So that loaded in all this data and made some other plots I already had. So that runs all code above. Which one, Briley, are you working on? Tell me which one you're working on. We probably will be checking that out. So Briley, let me know which one you're working on and we can take a look at that. Great work, Briley. And so now, let's make our model. To make this model, we have to know if the Y variable is quantitative or categorical. Because, and James, this is a good question, if it's quantitative, we'll do this regression. If it's categorical, we'll do this regression. So we are trying to predict last amount. So last amount is quantitative. So what kind of regression am I doing since last amount is quantitative? Last amount is quantitative, so I'm doing what? And great job, Lillian, right there. Excellent work, Lillian. If it is categorical, we'll use the GLM, which is going to allow us to do logistic. And Micaiah, just 320 jumping in here, doing some amazing answers. And we're going to use quantitative LM. Elementary school, secondary education, definitely. Did we do that one yet today? We haven't done it, but we can take a look. No, this is good stuff. And we'll try to do 2 right here. We'll try to do 2 questions because we might be able to do some quickly right here. But keep answering and asking questions. Notice how I'm just adding the names of the variables. I'm using copy paste to make sure I don't have any problems. Recent average and setting. Okay, so we need to include the interaction between these, and I'll add a star. Last but not least, y tilde x comma data equals, and the data equals homework 10 donor. And there we go. Y tilde x comma data equals. If we have time, can we do? Yeah, I think we'll do that next, Lillian. Thank you so much. I think that's on the list. Oh, this is not D? Is this the one you're wondering about? Is this not D? That's D, right? Am I going mad? This is the one I thought you were wondering about. Is this accurate, Lillian? Sorry for the pause right here. This is D, right? Summit 10, 1D? Okay, good. Okay. I was like, I need more coffee. Let's drop a coffee right there. I was so confused. There's the fit for the model right there. And now we need to look at a summary of it. Now, there are 3 levels to rural, suburban, and urban. Quick question right here. How many indicators will be created by rural, suburban, and urban? How many indicators are created by rural, suburban, and urban? How many indicators are created by rural, suburban, and urban? How many indicators? 2. Great job, Micaiah. Because one of them becomes rural, because the first alphabetical becomes the reference level. The indicators are always 1 minus total levels, so we know that there's going to be 2 indicators. Now, the output looks a little bit different too, and it's very large on the screen. Got it. Oh, there it did it. Because I have what's with the categorical variable, because I have a what's with the categorical variables. The categorical variable being setting, and there's the 2 indicators, but we also have something right here, which we were told to include. You can see it up here in the equation that it's allowing for the what with a quantitative variable. So these are it's going to change the slope of recent average, or the coefficient, which is the slope of the line. It's going to change the coefficient 2b3. I think we have it on the list. Yeah, we'll take a look. You got it. So this is a what right here. That thing right there is a what? What would we call that? That term is a blank term. Starts with an I. It's got an indicator. It's an indicator doing something with a quantitative variable. Well, it has an indicator. This is the indicator portion, and it's an interaction with another term. So the indicator is interacting with the quantitative term over here. That's what that stands for. This is the quantitative variable recent average amount, and then this is the interaction between recent average amount and setting urban. So when we do this, let's look at some of the questions. Write out the overall equation. This is a great way to go right here, and this is some really good stuff. When you write the overall equation, it's going to be a little bit long. What we want to do is we are predicting last amount. Last amount is equal to, and if you do the double dollar signs, you get the really nice writing right here. So how do we do it? Who knows my saying? Just start me off here with the little we're just going to algorithmically go through it and do what? How do we say it? Because if you get used to writing, you're like, oh, it's just and just watch as I do it and try doing it. Try to get the same thing. And we're going to see how to write this plus this times this plus this. Micaiah, great work right there. Once you kind of know it, you're like, oh, it's just this, which is the intercept, plus, it's going to be crazy long, plus this times this. It's going to be long. Plus, oh, we don't want to do that. Oh, does that work? Ooh, I just learned something. What am I on? I'm on this. It does work. Beautiful. Times this. It's going to be a while. Plus this. Times this. Plus. Next one's a minus, so we're going to do minus. The reason I'm doing minus is because the coefficient is minus. Plus this. Times this. I hope that, would this go off the screen? I hope it wraps. Next one's a minus. That's why it is plus, but it's a minus. Plus this times this, and that means it's multiplied by right there. Put it in actual math. Side note: we were interpreting the p-value for setting urban, and the output is says to give the new information relevant to the reference level Correct. Which one is that, James? Remind me which one that is that. Which question is that? The p-value would be, the p-value of setting urban means that it is significantly different from the reference level. So this p-value right here means that setting, oh, not that p-value, excuse me. This p-value right here means setting urban is different from the reference level, but that's not the drop one though. That's the summary, which compares it to the reference level. And that might be an earlier question that doesn't have the interaction. So there's the really long, crazy equation. And I'm a little, make sure it prints out properly. You might just go classic right here and write this right here. It is doing like some LaTeX writing right here. So maybe I'm going to remove out these and do the following. So this right here is the equation. Whew! That's not fun. Oh, and I left in the star right there. So it thinks when you're doing the star that you want to call multiple, you want to call bolding. So here's the full equation right here. But this is everything right here. This plus this times 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 this. And make sure to carry your minuses. So the next question says, we need to write it out for houses in the rural settings. And it sounds like this is a hard task, but if they're in the rural setting, that's the what. If they're in the rural setting, that's the what. If they're in the rural setting, that's the what. This is the easy one. That's the reference level, right? So that means all of this stuff down here, well, not account age matters. All of the other things like setting urban.
Notation, brother.
It doesn't matter.
I'm going to do that like 50 times. The other things don't matter because setting urban will become a what in this problem right now. Setting urban will become a what when we solve this. Setting urban will become a 0. Setting suburban will also become 0. All these things where you see the setting right now are going to become 0 because we're doing the reference level, so we're not talking about these settings, and so they all become 0. That was for the other things. It's for 201. We just made it earlier today. Leo suggested it. So thank you, Leo. We're going to work on it. So all of these right here are something times 0. Something times 0. Something times 0. Something times 0. So these are all going to go away. Does that make sense? Leo's awesome. Shout out to Leo. That's a minus for the other thing. So let's connect that back in here. But I don't want to solve this out completely. We just...
Notation, brother.
Wake everyone up with that. But does this make sense right here that when you're plugging this in, you're going to plug in zeros or ones for these indicators? So kind of talking through the other ones without completely solving them, but to explain what's going on here mathematically. Leo, they love it. When you're solving this, if something is setting rural, then it's not setting urban. It's not setting suburban. It's not setting urban. You would set these all to 0. So if we were to go here, and please reduce, I'm kind of not doing the full problem, but talking through it a little bit here. If I said solve for setting urban, what would you do? If I said solve this line, then you need to, well, the easy one is to solve for, because you just delete off these because they're all times 0. So the rural won't change the base intercept, the base of this and the base of this, like the original values. But if you were to solve for, and this is the important thing here, if you were to solve for something like setting urban, what do you need to do to solve for setting urban? We've been doing some Chapter 15 quiz. We're going to go back here in a moment, do it. And this is Makai right here, especially with setting urban, and make sure to reduce this. With setting urban, what do you need to do? Like if I'm going to solve for setting urban, what do I need to do? Plugging in ones, correct. And where do I plug in ones? Do I just plug ones in everywhere? Or do I just go 1, 1, 1? Oh, that's 2s. See, I can't even do 1s. Do I just go here and do 1, 1, 1, 1 like this? Do I do that? Is that what I do? I plug in a 1 for setting urban. So where I see setting urban, I plug in a 1. I see plug it right there. Am I done? Is that how I solve it? Am I good? And then I think Lillian's right there because now setting suburban, we're not in. Does that make sense? We're in setting urban. So I plug in 1 for setting urban. And then for setting suburban, I plug in zeros, which means those terms right there go away. And look at this. And then, like, I want you to finish off the problem. This goes away also. And, well, we need that minus. Well, it's minus minus, so we can just... We need the minus because that's the coefficient on this one right here. That's that one. And that's times 1, so that can go away. And this is times 1, so the times 1 can go away because that doesn't do anything to it. And what do you notice right here? What do you notice about this? Now, this is where you need to do a little more work. I might even make this look a little bit prettier right here. What do you notice about my equation? And what do you think I should do to it? Like, let me highlight some stuff. I'm just going to make it highlighted. What do you notice about those terms I highlighted? They could be what? Those terms I highlighted, I'm not saying multiply them. I'm just trying to bring your attention to them. Those terms I highlighted there, which I'm not going to do the rest of this. Those terms I highlighted there could be what? Basically, you could add them up, right? Because they're just two constant values. How about the terms I'm highlighting? I'm not multiplying them. I'm just highlighting them for you to see. The terms I'm highlighting here are also can be combined together to like make an equation, right? Because they're both this times, you can just call that x. Adding like terms exactly, and that's what we're doing right here. So it comes to algebra. And you want to combine like terms, adding like terms together. Does that make sense? And really good review, really good questions. So reduce your equation down into, where you've combined your like terms. Account age is all by itself. Why does account age have this constant value for anything I write? So explain to me theoretically, why does account age, great job right there, Micaiah. And why does account age, 100 points, Micaiah. Why does account age not have a different value whenever I rewrite lines? Why does account age have a same constant value? Like I can rewrite different lines and account age is going to have the same value. Account age will always have the same coefficient because there's no what on account age. Account age always has the same value in the model. It has the same constant value because it's not whatting with anything else. So account age will have the same constant value, same coefficient because it's not included in any sort of what. Where the other things have those in them, so they have different values. It has no interactions. Exactly. Great job, William, right there. It has no interactions. And that's the idea of like combining. Like it's not being combined with anything else, like interacting with. So good job, Makai, right there. It's not interacting with anything else. There's no interaction term on it. So it has a constant value in the model. And so anytime you solve out the model, account age is going to have that. But the coefficient of recent average amount depends on the setting we're in. Does that make sense? Like you're going to change recent average amount. It's going to be lower when you're in setting suburban. It's also going to be lower when you're in setting urban. So the coefficient of recent average amount depends on the setting you're in. Also, the intercept right here would depend on the setting you're in. Does that make sense? The intercept is higher when you're in these other settings because you would be timesing this by 1 and it would just turn into the constant value. And this is setting suburban or setting urban right here, which is where we would add this value as a constant to the intercept. So these change the intercept. Remember, indicators change the intercept, but interactions on indicators change the coefficient of the variable they're interacting with, which it's changing on recent average amount. Mine's blurring right there. Is that making sense? That's a big review. It's good concepts right there. We're going to come back here. We're going to do Leo's question. Then we're going to do another 320. Then we're going to try to do another 2-1. I think we got enough time. How's everyone doing? Can we do 1A and 1B? Assignment 11. Ooh, we might have enough time, Kyle. Stay tuned, Kyle. Great questions, Kyle. We're going to try. Let's try to do it. Hopefully that helps out a lot with those questions. I want to say a big thank you. Kyle, let's add that right here. I almost forgot what day it is. Kyle, such good questions. We have this. Thank you, everyone. Yeah, we might. I don't know if we have enough time today, Kyle. I appreciate it so much. I like to keep the list of the questions. Great job, Kyle. Working ahead right there. Nice job. We did some yesterday. Leo, you were wondering about the non-profit. Was it non-profit, Leo? Correct me if I'm wrong on this, Leo, as I'm finding the non-profit question. We're going to try to do your question. Thank you so much, Leo. Always being here. Always getting that notation.
Notation, brother.
I'm just going to overuse that now. It's non-profit. Good. Okay, let's go grab it. Here we got it. Non-profit school dropout rates. Here we go. Okay, we got the nonprofit monitoring school dropout rates. Now, with this question right here, first thing we do,
Notation, brother.
we get scared is what we do. And then we write down our notation. We just gotta hire famous wrestlers to say it. Someone help me with the notation. I'm gonna put some colors on the screen right here. See if you know the notation. That is a good way to make sure you get the problem right. So, what is the notation right here? We haven't done this one. Good question, Leah. What is the notation? I think that's everything. Okay. Leo is just leading the way right there. I think Leo, yeah, I think he might have it. Yep. This is the baseline, the proportion they think will drop out. This is going to be the amount they see drop out of their sample size of this. So they believe they would expect to see about 9.6 drop out from a baseline. So it's kind of saying like, well, in the past, we've seen 9.6 drop out. So that's kind of what we would expect. That's P0. It's kind of what we would generally expect to see if nothing has changed. Here's what we saw in our sample. 158 dropped out of 1795. So 158 is the amount of successes, and 1795 is the amount of trials, the amount of observations we have. The yellow I've highlighted is going to lead to the what. So there's not that much notation for this problem. We should probably, as we always do if we have x over n, immediately find our sample proportion, which is the percent we see in the sample. Remember, p hat is sample proportion because it's what we saw in a sample of size, whatever. So nice job, Leo. 0.88. I'm just going to take it right there. There's one drop, correct. One drop. And we need to talk about, we'll do some bonus. There's one drop. So if you got to drop one, it's all right. It's all right. There's one drop. But good questions right there, Kayla. Thank you, Kayla. Might be a busy week. So you might say, I got to use that drop. And that's why we have it existing. So Leo gave us the p hat right there. Is there any decimals, Leo? How does that round? I'm gonna throw another decimal on there. I'll throw another decimal. Oh, wow, Leo, I should have trusted you. Leo did give that last time. I'm throwing another decimal. Because sometimes these come down to little tiny decimals. So now when we do this right here, now that we have our notation, our first step is to write our what and what. I like to do it this way to make sure I know the practice of it and then can answer my Pearson questions. Try following along and writing this sheet down as we do this. Well, so they're asking, is there evidence that the tutoring program has been effective? Correct, Leo. Exactly. That's all right. If you don't have any drops yet, don't worry. Just relax. Say, you know what? I've earned this. I've earned a little bit of time to myself this week. And that's what you've earned. So don't worry about it. You've been following along in class. You know what? This assignment's more of a review of like introducing logistic. Next assignment's going to really focus in on logistic. So if you miss assignment 10 and it's your drop and you choose it that way, fine. But assignment 11 is going to really help like learn logistics. So I would focus in on assignment 11. So with this, Leo's pointed out the null hypothesis is always going to have the equal sign. So when you write this, you can always write the following right here. Oh yeah, you'll be okay. Yeah, Kayla, take a break, relax, and just follow along. Like next assignment, like be like, okay, I'm gonna take a break, and the next assignment I'm really gonna hone in on it. Or you could just do a little parts of it and get like, I think it'll be fine though, because I don't even think you need like a 40 or 50. As long as you do the next one, I think it'll be fine. So when we are doing proportions, we have the null that P is equal to P0. So Leo, can you write the null hypothesis here? Don't look at the my Pearson. See if you can do it without, because the more you can do it without looking at the my Pearson answers. So we know what P0 is, right? We've already identified P0. So we just have to write P equals P0 and put what P0 is in there. So remember, don't look at the my Pearson, because just try to do it without. Be like, okay, I got to write P equals P0. Do I know what P0 is? So what would the null be? Remember, it's P equals P0. And so what would the null be? Exactly. Great job, Priya, right there to the rescue. P equals, oh, careful. You used P hat, I think. Oh, no, Priya. What am I doing? Priya is 100% right. Be careful, Leo. You said P0. Priya, both great work there. It's going to be P equals P0. And P0 is this. Sorry, Priya, you were 100% correct right there. That is the right answer. So P equals P0 right there. Now, whenever we do the alternative, the only thing that changes is the sign. The only thing that changes is the sign. So if you write your null, you can write the alternative by just changing the sign. Now they're asking if this has been effective at helping students not drop out, which means, as Leo was saying, we'd want to see the true dropout rate is less than what it was. Does that make sense? Like, to say it's been effective means that we have decreased the dropout rate. So the sign for the alternative is a decrease we are looking for. We're doing all chapter 15 today, Zach. Woo! And then we're introducing type 1, type 2 error. All of chapter 15 will be completed today on Stat 201. Chapter 15 complete. Step 2 right here is to find your z, your t, or your chi-squared. The z, the t, or the chi-squared. Z or t or chi-squared. Do realize we have right here the step for it, the p hat minus p naught over the standard deviation of p hat, which is p times q, p naught times p naught, p naught times q naught over n square root. That's because we assume that p naught is the truth. So we'll write here that z is equal to p hat minus p naught over p naught q naught over n square root. And so now we have here, I think we can just, Leo does a great job on this. There we go. What is q naught? Who knows what q naught is? I always like asking that. A lot of people say, wait, how do I get q naught? And I say, wait, it's just 1 minus p naught. So we're going to take right here and do 1 minus p naught. And there's q naught right there. Remember, we just subtract. So it's going to be 1 minus. Those should add up to 1. Great job, Leo, right there. 100 points. Excellent work. Now we're going to take the sample size of 1795, divide by, and we're going to get the z-score. So this is just the standardized difference for us right here. Oh, well, I should have done that afterwards. Oh, is that the difference? The difference is tiny. The z-score should be negative and be small, which means to a big p-value. It's not going to be an effective program, I think. Okay, let's find out. No, sample size is large. There's a small difference, though. Yeah, z-score is like negative 1.3 or something. Okay. There's the standard deviation on the bottom. That's what we just solved for mathematically. And now that we have the standard deviation, we're going to take 0.088 minus 0.096. That's the difference. That looks to be mathematically... Wait, something seems off. Yep. Making math error. Something seemed off. I was like doing it in my head. I was like, that seems off. Make sure to do your math correctly. Math errors are the number one reason we miss problems. And there it is. And that was the z-score. I thought I should get something about -1 something because we saw it went down, but not that much. So the z-score is -1.15. From the z-score, I'm always going to find my what next. From the z-score, I will find my what next. From the z-score, I find my what next. The third step right here is from my z-score to find my what. What do I find next? What is the next step from the z-score? We're going to take the z-score, find the p-value. Great work right there. So we're going to draw our normal curve. And we're seeing if it's decreased. So we go down here, and we're at this value right here. I should have done it with a red line. Oh, good. And we're at this value right here. Now, I probably drew it a little bigger than it is, but still it goes to say, is that a small or large p-value? We'll find out the exact value here in a moment. Just look at it visually. This is where we landed, and we're shading less than because of our less than alternative. The less than alternative points to the left, so we shade to the left. Because just think about the way it points, the way you shade, the sign of the alternative denotes the way you shade on the curve. So we're doing the less than alternative, shading to the left of it, the less than, left. And so does that look big or small right there? Does that look like a big or small p-value? And then we're going to show it on the applet. And we're going to see something probably pretty similar to us. We should. Does that look big or small? It's going to be about 14%. Go look where that one went. No, it's going to be about 12%. So we're going to go below and put in the value. 12%, I say. And there's 12.5%. Nice job, Priya, 100 points. Great work finding it. 12.5 and then 12.51, but it probably... Oh, I think I had this Great job, Priya. Excellent work. And so it is 12.51, 12.5. It's still large, which means we're not going to reject the null. And that's the fourth step. Now that we found the p-value of 0.125, which is the probability of our result, or a result more extreme given the null is true, i.e. the p-value, we'd go right here. Now, I'm assuming an alpha of 0.05, which is our rejection criteria. Is our p-value in the not reject region, which means it's above, or is our p-value in the reject region, which means it's below? Now, technically, if it's at or above, it's in the not reject, and below is in the reject. I don't like to do exactly, but is our p-value of 0.125, is that above, and that's the amount of area, is that above the rejection region or below? The alpha is the when we reject. So is this a value higher than? We would not reject, i.e. statisticians like to say fail to reject. You just say, I don't reject the null. I'm going to not reject that. And we'll see if it uses a different, it'd have to use a crazy alpha level to not do it. So that should be all the answers we need right here. Lots of different things. We need to find the equal sign, and they're trying to show it's decreased. So there it is right there. There's the right null and alternative. Compute the test statistic. That is the z, the t, the chi-squared. So they're just asking you to compute the z-score. It should just say compute z if they were being nice. There's the z-score. Compute the p-value, 0.125. That's what we got from the David M. Lane. Is there experiment evidence that the tutoring program has been effective? No. Because what we saw is not that unusual. The school's district's observed dropout rate would not be unusual if the dropout rate was still this. We conclude that it has not been effective. 4 decimals. Oh my gosh. Oh, whoa. So, woo. Leo, I'm so afraid we're on a streak today, and I feel like this is, I know, right? We'll see. We'll see if it would get mad at me. But that's a lot of decimals, right? I'm scared, Leo. We've been on a streak here. Oh my gosh. Well, let's see. Leo, did you save the day, Leo? Whoa. Leo, I'm still giving it to you. I'm still giving you 500 points because that is like the #1 way to miss problems. 500 points, Leo. Yeah, we're lucky. There's probably a little wiggle room on these questions. Notice how it's still saying I'm right here. It still gives it, there's enough of a wiggle room. It does say 4 decimals, but it's got a little bit of a little give on it. Probably a little give on this one too, depending on how you carry decimals. Oh, it's mad about that. Yeah, so you have to get this one on the dot. So make sure to carry your decimals there. Hey, hi, Officer. Hey, Kristen, good to see you. Can you explain the last one? Sure. So what they should just be saying is, do you reject the null or not reject the null? And the thing is we do not reject the null. So think about this. If we don't reject the null, that means we think that the true dropout rate with the program is still this. Does that make sense, Leo? Like, I do not reject the null. I think that the dropout rate has stayed the same. Does that make sense if I say that? Like, I do not reject the null hypothesis. I think the dropout rate has remained the same. Does that make sense? Tell me which one's Priya, because remember the quiz changes versions. So let me know which questions those are. I do not reject the null. So I do not reject the null hypothesis. I think the dropout rate is still the same. Does that make sense? I do not reject the null. Like if you do this right here, I do not reject the null because the p-value is higher than 0.05. I think the dropout rate has remained the same. Like I don't have evidence that it's decreased. So you do not reject the null also, right? So your p-value is even higher than mine, telling you that what you saw right here, and this is what the p-value tells us. The p-value tells us how likely this result right here is. The result we saw, which is in our sample, was very likely. Political ad and jury. Try to do that one right here, Priya. So the result we saw in our sample was not unusual. That means likely. So they're just doing a different wording to say it's not unusual. And since the p-value is high, like if I told you, Leo, I say there's a 29% chance you'll win the lottery. Would you say that that's unlikely that you'll win the lottery or not that unlikely? Now, I know 29% isn't like very likely, but if I said 29% chance you'll win the lottery, what would you say to me? You'd say, oh, that sounds like it's quite possible, right? Like, I'm not saying it will happen, but sounds quite possible that I could win the lottery today if there's a 29% chance I'll win the lottery. But what if I told you, if we did a different p-value, and I went over here and I said, the probability of you winning the lottery is this right here. I mean, you might still like it. But now, if it's 29%, you'd probably say it's likely, right? But if the probability was this, you would say the probability is unlikely. Like this is an unlikely thing right here. Where if we go to, did I do 2/3 there? Where if we went to something like this right here, this is very likely. Now, I'm not saying it's going to happen, but this is something that, yeah, sure, I guess that could happen. Does that make sense? Like, if I tell you there's a 21% chance of rain today and you have a big interview, would you grab an umbrella? Like, let's say you have a big, important interview today, and I say there's a 21% chance of rain. Would you be like, oh, it seems possible it could rain, or no, it's not going to rain. There's no way it's going to rain. You'd be like, I'm going to grab an umbrella. But what if I told you there is a 5 in 10,000 chance it'll rain today? Would you be searching for your umbrella? Be like, I got to find my umbrella. 5 in 10,000 chance it'll rain today. So the probability or the likelihood of it raining is 5 in 10,000. Would you be like, it's pretty unlikely it's going to rain, so I think I'll just forego the umbrella because it seems unlikely that it's going to rain. So if you think about these as probabilities of what we saw given the null is true, this would be a very unlikely thing to see given the null is true. Where this, we're not saying it, like it must occur, but saying, that seems probable, like that could occur. That seems likely. Like it could happen about 21% of the time if the null is true. But something over here would only happen 7 out of 10,000 times if the null is true. So we're like, yeah, that doesn't seem like it would occur if the null is true. Seems very unlikely. I mean, it could occur if the null is true. Like it could rain today, but I don't expect this to occur. This is very unlikely to occur. Does that make more sense, Leo? And that's what the question is getting at the final thing right here. The school's district dropout rate was not super unlikely. I mean, I know it's low, but it's not super unlikely. And since what we observed was kind of not unusual, given the null is true, we cannot conclude it's been effective. So we're concluding that it's not been effective, basically saying the dropout rate has remained the same. Because if the dropout rate has dropped, it's been effective. So the null could be the tutoring program is not effective. The alternative can be the tutoring program is effective. Good question right there, and especially with the wording at the end, understanding conceptually what we're doing. Yeah, I think it was around. Tell me about if there's a rounding error, just email me and we'll fix it right up. Great job, Leo. Woo! We're gonna try to do one more 201 and one more 320. Good practice. And remember, try to understand what the questions are asking, because solving just the question's not enough. Leo, I want to give you a huge shout, another 100 points, Leo, because if you just solve the question, click the buttons and get it right, then it's like, what are we doing? 97% is good enough. Great job, Leo, right there. We want to understand what the questions are asking. And that's why we went into that little extra bit right there, making sure we understand why we are doing certain things. Let's talk about some why logistic regression. The why helps solving for the test, because you see different questions on the test. It's not going to be the exact same questions. We have to know why we're doing this, what it means. All the mu bucks given out. So we're going to do some 320. People were wondering about question 2, B3, and B5. Okay. Oh, cool. Let's do this. We'll do different versions. I'm going to do different versions of these. I'm going to try to like mix it up. 113. 40. Here we go. Doing some 320. 320. Let's do it. Okay. So I'm going to kind of do a little different version. You're like, oh no, do the exact question. I'm sorry. A little different version right here. Here we are doing some logistic. We're trying to figure out for the Titanic. 1D? Oh, we did 1D earlier, Joseph. Check it out. Earlier in the video, writing the equations, we were doing that earlier. So check out 1D right there. That is at the 38-minute mark. We spent a good 17 minutes writing out equations. So check it out. Good stuff, Joseph, right there. Yeah, thank you, Makai, right there. And so first calculate the analytic value of age, where someone has a 50% chance of surviving. It's pretty funny. Well, it's not funny. It's just interesting Titanic questions. Let's try this. You ready? Let's do similar question. Similar question. Well, I think people are wondering about... Oh, B3. Good. This is it. Okay. So I'm going to predict... yeah, awesome. DM. Oh, I'll check the DM. You got it, Leo. Thank you so much. This is a similar question, not same work, but it solves how to do it. We are doing logistic, which means we are fitting the what shape curve to this. We are doing logistic, so we are fitting the what shape curve to this. We are doing logistic, so we are fitting the what shape curve to this. Who can help out right here? We are doing logistic. So the shape or name of the curve, sigmoidal S shape. So we have to do the GLM right here, and we're going to kind of work off problems we did yesterday. Let's use weight today. There we go. And comma data equals. This is not the same thing you're doing, but very similar. And now you have to do family equals binomial. And we're going to have it autocomplete and delete that. And there we go. We've created a logistic model. Now, when you do, no, that's fine. Micaiah, that's excellent. Sigmoidal, that's perfectly fine. Sigmoidal, I don't know how to spell it either, so we got it. The sigmoidal curve looks like a what? A very strong sigmoidal relationship looks like a what? A very strong, visualize, a very strong sigmoidal curve looks like an S, sigmoidal S. So this is a very strong relationship. You might not know this, but weight has a very strong association with predicting if somebody is male. S. So think about this. I can predict whether or not Brian is male based on his weight. Now, why are we predicting male and not female? And this model was done with male, female as the two values to predict from. So this was the data we collected in survey 10 right there is from 2010. So why didn't we predict female? Does anyone know? It kind of goes to how logistic works. Why not predict female? Why are we doing probability of male? So when you think about this right here, the way it works is female, male, and I've written them alphabetically. So why is it saying prob male over there? Not quite the reference. Not quite the reference. It says you can just pick the one. Good question, Alex. You can just pick from it when you look at it. Great question. I'm getting external error. People are saying that go to the site. Someone else had the same error. So go to the site right here. Abby, we got to look into this. I probably my email might be blown up. Go to the site right there. I might even need to send in an announcement, but you're the second person to say that, which worries me now when two people say it. But try going to the site and log in, do sign in. We were able to fix the problem for someone else with that. Thank you for mentioning that. It's not quite the reference. Reference is when we talk about indicators. And if you have, so we only have the one model right here. If you're doing indicators, then I got that issue too. Try logging in right there. And we might not have enough time for the twins problem. We did that one yesterday though. So we're going to we'll do one more Mike Pearson after this. Good questions, everybody. Let me know if you can't find one. I can send you the videos. But we're going to try to do more right here. Is the assignment due tonight? Sorry, I'm thinking of which ones. Maybe I'll do a little more extra office hours a little bit later. If it's due tonight, if it's due tomorrow, we'll be doing a lot tomorrow. So with this, if I say reference levels, we're talking about a what variable? It's due tonight. We should have done. Oh, you're talking about this one, right? 320, right? 320 is due tonight, and then you guys have time to do Sunday. Which one? The twin one? We'll try to do that, Sophia. Thank you, Sophia, so much. So if we have reference levels, we're talking about a what variable. This is key stuff. If I say reference levels, I'm talking about, and this is reference levels right here, I'm talking about a what variable. If I say reference levels, well, so these are all, the rural is the reference, and these are indicators. References, and I think do we still have the notes from yesterday? We don't. References are categorical, and then they're categorical X's. Does that make sense? References are the first alphabetical for categorical X's. But in logistic, think of all your L's. In logistic, this is known, haven't gotten it yet, Brianna. Good questions, Brianna. I think we'll probably do that a lot tomorrow. Good questions, Brianna. Thank you so much. 100 points. In logistic, we're talking about the Y variable has a what? A level of what? In logistic, the level of this is last. In logistic, the level of this is last. And I don't really call the other one the reference level because it's the not level of this. In logistic, that over there is called the what? The level of what? Yeah, definitely, Brianna. You're welcome. In logistic, well, so it's called the what, though? It's called the level of what? So I'm interested in predicting that. So we call it the level of this. In logistic, the level of interest is last. Does that make sense? And we predict the probability of it. Does that make sense? We would have the probability someone is male. So in logistic, the level of interest is last. So the reason we're predicting probability of male is because male is last alphabetical. Does that make sense? And I don't talk about a reference level with this. I just say the one I'm predicting, which is the level of interest. And it's just arbitrary that it's last. So we predict the probability of male because male is last alphabetically. So all of this right here, predictions from the model, will be probabilities for males given their weight. So when you look at this right here, can you just look at this visually and tell me at what weight or close to what weight would you predict? And this is a good way to make sure you get the other question right. Now, don't just go straight from this, but at what weight would you predict somebody is male? Like at this point, you would say, it's more likely they're male than not male. So at what weight would you start saying, more likely male than not male? We wouldn't go around doing this for our friends or anything, but this is the way mathematics work. What weight? 160, good guess right there. Great guess, Lillian. And if you trace down, that's probably about where it's at, a little more than 150. Great job, Kristen, following along. And so we can solve this actually by taking from our summary right here, we can take the intercept and divide it by the negative slope. Either one, if you make them both negative, make sure they are different in sign, and then make sure you kind of see where it would about be at. And when you run it, look at that. Does that look like the right value? I would say it does. And you can even confirm by going over here and go to AB line and do a vertical line. I have to think for a second and add it right there. And there you go. So this is what you want to see. You want to see that you found that value. And the way to find this is going to be the negative intercept over the slope. Does that make sense? I took the negative intercept over the slope, and thus we have found it right here. You might be on another account, Catherine. But does that make sense? 320 right there, how to find that kind of flip point between when we predict one versus the other on the sigmoid curve. Oh, no worries, Catherine. I was like, I think so, because you're not a mod and then you don't have any hours, so no worries. This is how we find that flip point right here. So Joe Black is 32. What does the model predict for the probability he did survive? Let's change this to say Brian weighs 180 pounds. What is the probability he is male? How do we know if it makes sense or not? Does it say if it makes sense? What does it say? Then come on whether this number makes sense. Well, think about this. With whatever number you find right there, does it make sense that after 157, you would think somebody, sorry. Does it make sense that after 157, I'm going to throw 1,000 points if you're within 2%. Kristen has I'm just going to throw 1,000 points. I love that Kristen's following along right here and taking some really good educated guesses, because I think Kristen, if you solve that out mathematically, that's amazing. I might throw another 1,000 points. But Kristen took a really good guess right there, it looks like. And I'd say this makes sense. So when we comment if it makes sense, we're basically saying that basically after 157 pounds, you would think somebody is more likely male than not male. Does that make sense? We did it yesterday. We did it yesterday, Caitlin. Good question. Don't worry, Kristen. That's great work. And actually, the way you're doing it is probably the way you should do it first, is to just look at it. Because you're literally, I'm assuming, Kristen, you went here and you said Brian weighs 180. And so if you go over here, we could go here and add a horizontal line. And you were estimating that Brian is going to have about an 80% probability, and you were super close. If you notice, we're going to have to lower this down a little bit. Brian has about a 78.6% probability. It might even be a little bit lower. But that is pretty much, we can see how close we are. But you were very close. Good guess. Maybe it's like 70. My probability of being male is about that. I need to gain some weight and be more likely to be male. But it's about 77.6. And you were doing this here with your eye being like, let me go up. Let me trace over. Now, that's not the exact way we do it. We're going to see the exact way here in a second. But we can kind of visualize it and see where, Brian would be at 180 pounds by going across and marking the graphic. We could do it ourselves with crayons and stuff. I got crayons, what I was saying. That's a great way of doing it, because here's where the mistake happens. Because let's write the model. And if we write the model, this is where things are going to get interesting for those who know 201. Remember that when we write the model, it's y equals b0 plus b1x. Hopefully people remember this. Yes. And make sure to do GLM. Oh, you might have a pretty flattish line, Lillian. It might be that it's not a strong relationship. Make sure you're doing GLM family binomial. Lillian, if you want to send me it, I'll check this out. Make sure it's GLM family binomial. Kaylin, I'll find the video here in a second. And then, we'll find the video for you. You got it. And so we have here the intercept. The intercept is this value. And then the B1, which is right here, is this. And then we have weight. Now you have to be very careful because it might look like a line for you. I might even check it. It's not very S-shaped, then it's a very weak relationship. The p-value might even be pretty high for it. So the p-value might be very high. I might even take a look at the answer on that one. If we are going to make predictions with this, what do we then do when we get this y value? Because here's what's going to happen that's weird. When we take this and I plug in the value of Brian weighs 180, I get 1.22. Now that's not the answer to Brian's probability of being male. We just found the what right here. We just found the logit. So who remembers from class what we do once we find this? Once we find the logit, we have to put it through a special equation that turns it into an actual interpretable probability. So we have to take this logit value that we solved from the regression equation, and we go right here and do what with it? What do we do with it? We're going to do one more to one at this. I just an announcement. What do we do? Turning it. What do we do? So we take this value that we found. There it is right there. And we do what? We have to do the e raised to over the 1 plus e raised to. So remember the equation. It's simply, yep, the e thing. Great job, Lily, right there. It is the e raised to over the 1 plus e raised to. The e raised to the regression over 1 plus e raised to. And this is how logistic takes the logit and turns it back into the probability. This is bound by a 0-1 curve because we're not doing linear regression anymore. We're doing the logistic curve. And if you zoom in on a logistic curve, like if you only have a small window, you might see what looks like a line, but it is a logistic curve. The notes kind of mentioned that sometimes it looks like a line, but if you expand your view on it, it's just that you're seeing like part of the curve. You're not seeing like where it makes more of an S shape. So if you expanded that window, you would then see the logistic, the sigmoidal curve. But it has to be bound by 0 and 1 via that equation. So if we take this right here and we do exp, and I've stored it as x over 1 plus, remember we should see the probability we saw if we've done this correctly. We should get about 77.6%, and there it is, 77.3 is the more exact. And we could take that value and drop it in to our graphic and see that we landed right on right there. So that is the decimal place accurate as far as we can tell. Brian has a 77% probability of being male, weighing 180 pounds. And great job right there, Kristen, also kind of taking a good guess at the answer to see what we should get close to. Just to confirm very quickly, and then we'll mention to one, let me send the announcement. Gotta remind everybody about class. Please come to class. Attendance been kind of low lately. Whew, a little chill music right here as we finish up. And I'm going to try to find videos for people. Let me send the announcement for class. Busy office hours. Okay, grabbing the video. Nobody's tuned in yet. Class in 20 minutes. See you soon. There we go. Class number 27. There we go. Okay, video sent. And so now, do we talk about 5 prime ways? Oh, then it's just done. I think it's a good start to this question. Good start. Let me look at the other curve. I'll show you right here. Let me load up the points. Sophia, good to see you. Titanic. Okay, so M save into GLM survived. Age. There we go. Look at you. Welcome, Makai. Great work. And I don't want to quite give away all the answers, but I want to see it. Yeah. Oops. One button. Yep. This is logistic curve. So pretty interesting. This one's going to turn out differently. What do you notice? I got to work. You're welcome, Abby. Great work. What do you notice? I think we can change the x lim right here with a vector of x lim. What do you notice about where the breakpoint is? What do you notice about this? So making it look more like the logistic. But what do you notice Now, these are ridiculous values, but there's the logistic curve. I'm just kind of zooming out on the x-axis right here. What do you notice about where the breakpoint is? And I can kind of make it more clear if I do this, which is something you should find with your answer. What do you notice about where the 50-50 breakpoint is? Kind of something you should see mathematically here about the age of an individual who would be more likely to survive the Titanic according to this model. So yeah, Lillian, that should make sense. And thank you for people for saying, hey, can you look at this one a little bit more? Can you do our kind of art a little bit here? Because that kind of helps show by going through here and changing the graphic a little bit. What do you notice about the age of someone who would survive the Titanic? The person most likely to survive the Titanic are the people likely who we'd predict would survive would what, which is very weird about this model, which I think the question is getting to when it says this right here, which kind of alluding to the answer to that. Because as people were commenting on this, I kind of realized what the question was going towards, which should definitely be commented on, which we're kind of giving that away. And you are correct. That is correct. Younger people, ooh, right there's the interpretation of the coefficient. People who differ by age by 1 year, people who are younger would be more likely to survive. People who are older would be less likely. But in Kristen, great work, and excellent work, Kristen, right here. What do you notice about when someone would have a 50% probability of surviving, like higher than 50%? So you are correct. It's younger people, but look at the age right here. And then I'll make the age range a little bit more reasonable to like how old people actually live. And then we'll show the ridiculous graphic again. And what do you notice about the age at which people would be predicted? Not just infants. You're on the right track, Kristen. You're on the right track. Not just infants. Because look at what I have to do to the number line to get the above 50% probabilities. Look at what I have to do to the number line to get the above 50% probabilities. Which I guess, I don't know, theoretically. Look at what I have to do, which this is what the question is alluding to. So here's a reasonable age range, but to visualize people who would have above a 50% probability, I have to do that. Remember, this is age, so we're literally talking about people's age. So think about this theoretically right here and why this really is kind of like, yeah, I don't know about that. Because we're talking about someone's age, how old someone is, and we have to show this theoretically right here to get values. So this question's kind of neat because it alludes to this. So what do you notice about it? And I think I'm head to the main screen here and then find questions for people. What do you notice? Does anyone notice it for 500 points? Kind of give me the answer. So here's reasonable ages, and here's where we can see above a 50% probability. So there's reasonable ages, 0 to 90, and then to see above, you're so close, Kristen. I know this is why it just doesn't make sense. You're on the right track. Interval, random 10%, and then the third one depends on the type of the variable. Alex, good questions. Random 10%, and then success failure. Kristen, yeah. I mean, so they're not even born yet, right? Because their age would have to be negative values. So that kind of gives away it's below 0 years old. So that's why it doesn't make sense to say like people who survived the Titanic would have negative age. Like they're more likely to survive than not. So the model would predict people who have negative age would have a height that would be above a 50% probability of surviving. So it doesn't even make sense. It's not intelligible to talk about the people who would be likely to survive than not survive. These are the kind of ages right here, 0 to 90. And here we'll head over. Apparently, according to the model, the math doesn't have to be logical. It just gives predictions, and exactly, well beyond that exactly. So that's what the math says. Okay, we're gonna drop some links in the chat right here, and that's what it just doesn't make sense. Math doesn't, if you run math equations, sometimes they just don't make sense. So Alex, the conditions depend on the variable type we are doing. If it's categorical, we're doing success failure. If it's quantitative, we are doing nearly normal. And I think there was a question on the airlines, was it? Someone was wondering about airlines. Caitlin was wondering about airlines. I did airlines yesterday morning. I think airlines was yesterday morning. Let's go find yesterday morning's office hours. 14 people watching. Hey, 14 people. Office hours from yesterday morning. Flights. Here we go. Airlines. And do remember, check out any of the videos. If you go to the video, and huge shouts to so many people. We already have 890. Holy mackerel. We get more views on office hours than we do class. Maybe I should just work problems in class. Hey, past Brian. I need to shave. So there's past Brian right there working the problem. And we did a lot right here. Sometimes problems can be a little longer than increasing the wrong font. Maybe I should just work problems in class. Maybe that's the theme. But there you go. What is changing? So here's what we did yesterday. You can see we did the cookies problem, the shopper problem. Is that the wrong? Hey, that's you. Oh, we're in the chat. Or is that a different flights problem? That's confidence intervals for flights. We can try to speed run one right here. Oh, that's the wrong one. That's the wrong one. Organization monitors. I need to move this on top of my list. Let's try to do flights real quick. You're in the evening one? Awesome. Let's try to do the flights problem really super quick. You ready? Let's speed run it. Speed run flights question. Airline question speed run. We got like 5 minutes. Flight one's different here. Caitlin, thank you for staying till the end right here. We're gonna speed run this problem. So I've got to we got to teach in 12 minutes. So we're gonna try to speed run this. So we're gonna do this quick. We can come back. Another officer has do it more slowly, but we're gonna try to do this quick right here. So let's do this. You ready? Oh, I don't have it up. Okay, give me a second. Let me go find it. Timestamp this. Okay, startup company. We're gonna try to speed run this. I'm gonna do it very quickly. So stay tuned. Oh, just kidding. Yeah, I think it's right. There's multiple flight questions. So this is gonna be a test on a flight question. Public relation. Here we go. It's luggage. Okay, here we go. Time to go quick. Gotta go fast, as Sonic says. Are the assumptions met? We need to do random 10% success failure. People were wondering about the conditions for confidence intervals, and it's the same for tests, random 10% success failure. We have it on here somewhere. We did it yesterday talking about the conditions. Here it is. Make sure when you do the third condition to know if it is success failure. It's because it's categorical. If it's nearly normal, it's quantitative. And so you always pause when you get to the third condition, random 10%, and then check the third condition. The null hypothesis, we believe right now that they claim 91%, so we're going to say that is the claim right there. So we're going to go with them claiming that is the truth. And so we are going to say that it's less than. This one sometimes gets me. They're saying, because when we're casting down on it, we're saying, no, you're not meeting that. So we're going to try to say that they're getting less than that, which is going to make big things. The z-score is going to be, we need to find p hat. P hat is what we saw in our sample. So this is the sample proportion. Does that make sense? That's the sample proportion. So sample proportion right there. Now we need to find P naught, Q naught over N square root. I am doing this equation right here. P naught was 0.91. Q naught is 0.09. So we plug in right here. I'll write it in this one because we only got seconds. 0.91 because that's what they're claiming is true. We're timesing that by 0.09. And the sample size was 717. So this is going to be the bottom of the equation. Oh my gosh. And so we're finding the standard deviation. Let's find that. So 0.91 times, oh my gosh. There's the standard deviation right there. That's what we're going to divide by right here. Now we need to take the difference, which is 779 over 117. That's the p hat. Please tell me if I make a math error. And that's the p hat right here. And the p naught is what they claim. If you notice, that's a pretty big difference. With that being a pretty big difference, when we divide this out, we're going to see that there's going to be a large z-score. So we subtract 0.91 from this, and that's very large. We divide by 0.026457. There's the z. That's ridiculous. Negative 8.87. That's insane. Negative 8.87. Yeah, so that's so far off the curve that basically the p-value is 0. It's so far off the curve. KP, thank you for asking. I think, is that the KP right there? I think we did it in another video. I don't think we've done it today. Did we do it today? Because we have officer. We did it yesterday. I'm 99% sure we did that one yesterday. We can come back to another officers though. So if you do below this one, because we're speed running this one right now, it's Z0. It's so far off the curve. It's like, no, I think you're wrong, airport. Do the results of the survey cast doubt? Yes, because the null hypothesis was rejected. Right there. Do we get it? Woo! Scary right there. Does that make sense, Caitlin? Quick run right there. 9 minutes. You're welcome. Yeah, and let me find that video for you. You're wondering about the organization monitors one. I know we did that one yesterday. So let me go find that, and I need to end this stream here. So organization monitors is in yesterday's stream. I know that. I know we did that one. Oh, found it. So here is the organization monitors. The nonprofit. Have we done the nonprofit? Let me see if I can find that. First link is organization monitors. Nonprofit. Did we do the nonprofit today? Yep. Oh, they're on my roof. I was like, what's that noise? I just keep forgetting they're doing the roof. Nonprofit is in today's video at the 55-minute mark. The nonprofit one right there. There you go. I will see everyone here in a little bit for class. Thank you so much, everybody. Great work. Just jump in, ask those questions. Yeah, no, the Z is pretty crazy, which means their claim's ridiculous. Good work. I think we got most of these done. I don't think we did philanthropic. And sorry, assignment 11. Thank you so much. I think it was James came by and asked this one. We'll keep these on the list right here. But a lot of work today, as you can see it coming up for the afternoon class. See you in a little bit here. 7 minutes. I'm going to go grab some food. Ah! Why do I scream? I don't know. For ice cream. That's why everyone screams.